Today we talk about conic sections. Yes, ellipses, parabolas, and hyperbolas. Apparently slicing cones was not enough suffering. So people invented several definitions and made all of them equivalent. In analytic geometry or calculus, people often start with distance definitions. An ellipse has constant sum of distances to two foci. A hyperbola has constant difference. A parabola stays equally far from one focus and one directrix. Another popular definition uses eccentricity. Take the ratio of distance to a focus over distance to a directrix. If that ratio is less than 1, you get an ellipse. If it equals 1, a parabola. If it is greater than 1, a hyperbola. Now here is the linear algebra definition. Start with a standard model curve, and apply an affine transformation x maps to ax plus b. Every ellipse can be obtained from the unit circle. Every parabola can be obtained from y equals x squared. Every hyperbola can be obtained from x squared minus y squared equals 1. If the matrix A is invertible, the conic stays non-degenerate. If A is singular, then degeneracies can happen, such as a point, a line, or a pair of lines, because geometry also enjoys edge cases. Here is the point. Start with the standard curve on the left, then apply an affine map, and you get the conic on the right. The algebra changes, but the geometric type stays the same when the matrix is invertible. So from this viewpoint, ellipses, parabolas, and hyperbolas are not mysterious separate species. They are affine relatives of three standard model curves. Now bring in polar decomposition. Write the matrix as U times P. Then x maps to ax plus b becomes U of px. Then plus b. For an ellipse coming from the unit circle, the positive definite part P does the stretching. The orthogonal part U rotates or reflects. Then the vector B translates the whole picture. The same idea works for parabolas and hyperbolas. Polar decomposition tells you what the linear part is doing geometrically, instead of leaving you alone with a pile of entries and false optimism. Finally, conic sections are exactly the plane curves defined by a quadratic equation in two variables. In matrix language, that equation becomes x transpose qx plus l transpose x plus c equals 0. Where q is symmetric, the quadratic form x transpose qx is the part that really matters. After a translation and then an orthonormal change of coordinates, the symmetric matrix Q diagonalizes. That reduces the equation to a standard form, which is why quadratic forms and conic sections are so closely related. So conic sections are a nice meeting point of geometry. Affine transformations, polar decomposition, and quadratic forms not bad for curves people first met by cutting cones and naming things. Dramatically,